Ramalingam sir, and respected correspondent sir, Dr. S. Karthikeyan sir, whose dedication has played a crucial role in charting the course of our institution towards excellence. So next, I would like to welcome our eminent resource person, Dr. Muralidharan sir, Associate Professor, for this wonderful session. A hearty welcome to our dedicated principal, Dr. Jayaprakash sir, and our energetic CEO, Dr. N. Prasannan sir, and our Dean, Professor P. Malarvali ma'am, for this wonderful session. So, and also I would like to invite all our participants to join in this session. So it gives me an immense pleasure to introduce our chief guest, our research person, Dr. R. Muralidharan sir. He is currently working as an associate professor in the Department of Materials Physics at Savitha School of Engineering in Chennai. Dr. Muralidharan sir holds a PhD in physics, awarded August 2004 from Anna University, Chennai. Throughout his academic journey, Dr. Muralidharan sir has been actively involved in cutting-edge research, specializing in diverse areas such as peroxide solar cells, photocatalyst, low-dimensional materials, and graphene related materials. His expertise extends to thin films fabrical through pulsed laser deposition and multiferic nanostructure, single crystal growth, and sustainable energy materials. With a commendable postdoctoral experience spanning various prestigious institutions globally, including the University of Leeds in UK, ICMAB in Barcelona, Spain, and Postec in South Korea. Dr. Muralidharan sir has granted a wealth of international exposures in his experience. As an educator, he brings over 12 years of teaching experience to his current role as an associate professor from Savitha School of Engineering. Dr. Muralidharan sir has demonstrated his commitment to academic membership by supervising PhD students at both Anna University and Bardiyar University. His significant contributions to this field are reflected in his prolific publications record with 54 research papers in SCI journals and H index of 20 and remarkable 1,340 citations. Please join with us by welcoming Dr. Muralidharan sir, a distinguished researcher and educator, to share his valuable insights with us today. So now I will hand over the session to Dr. Muralidharan sir. Please take them, sir.
Thank you, sir. Thank you for the introduction. I will share my slide. Just let me share my slide first.
Yeah, sure, sir.
Yeah. So can you see the slide, sir?
Yeah, yes, sir, of course, sir. It's visible,
Okay.
sir. Yeah.
Yeah, fine. Thanks. So again, I thank the organizers for giving me this opportunity to share my knowledge to this wonderful people. I have been attending all these talks for the past 5 years from the eminent people, both from the industries and from the uh, academic side also. So I appreciate the organizers to organize such a FDP with the industrial people also coming inside. And then the industrial people, I thank the industrial people who gave wonderful talks for the past 5 days, who said what they need from us, from the academic people. So I appreciate the organizers to organize and organizing such a nice FDP. And I wish such a kind of FDPs and workshops and seminars with both the people from the industry and academic people together, so that we will know what they need and let them know what we are having, we can produce. Okay, so with that short introduction, I want to start my presentation. So today I'm going to talk about the development of materials for industry applications. So I'm coming from material physics department, and I've been working in the materials for the past 25 years. So I'm going to give a very brief introduction about the importance of materials in various applications, especially for the industry for I think so, the industrial revolution, how the materials are useful. And before that, this is our campus, which is situated just on the outskirts of Chennai. Um, with a huge area, and close to our campus, if you see, there are quite a lot of industries as it is outskirts. This institute, so with a university, it is surrounded by quite a lot of universities. So most of our research are closely related to the industry for the application of industry. Okay, so with that, let me enter. So before starting, let me give a brief introduction of the need for materials. So the civilization, the historians name the development of a civilization on how we can use the materials. Okay. Initially, the 4,000 years back, it was called as a Stone Age, because we know how to use these stones. We know the different properties of these stones. We know that some stones will give fire if you friction by friction, and some stones are very hard, so that they can use it as a knife, and some stones are very soft, and there are some stones which can even show the direction. That's the magnetite, okay, Fe3O4. So the first scientific application for magnetic materials started right from the Stone Age. Let me not get into the details of that. And later on, when we know how to use the metals, it is called as a metal age, and it can be classified as both Bronze Age, Iron Age, and then we know now how to use the steel, and it is a steel age thing. Quite in this FDP also, the industrial people, I think the third talk was on the steel technology. It was wonderful. So we know all the properties of the steels, and recently it is the semiconductor age, silica age, then the space age. Now we are ruling the space. There is a tremendous fight that who can rule the space. So that's why India is concentrating more on satellites, more on the satellite missions to explore the mission, explore the space, because they will be the developed countries. For all these things, we need materials, different types of materials. The recently it is like nanotechnology, biotechnology, information technology, and artificial intelligence. For all these things, the materials are needed. Okay, so the materials are the basic thing for our development. So in this talk, I'm going to give a very brief introduction about the importance of materials, and how these materials can develop our technology. So let me uh, start from a very basic example. Let me start from the mobile technology, which we are using almost uh, daily. So I took this image from as a model, which is going to be released next month, which is this is a Samsung Galaxy. So what we need in this mobile technology. So this is the front side. So we need even on the screen to write. Okay, so we need a notepad kind of thing. So that can be uh, used as a notepad, and our screen needs to be sorry, our mobile needs to be so thin and so weightless. And on the back side, if you see, we have a camera and LED. Okay, so for all these things, materials play a major role. So if we split the mobile, okay, our mobile phone, or if you, it contains so many layers. So the first three layers is the display technology, related to the display technology. So you have a Corning glass, and then a capacitor, okay, and then we have uh, the processor side. Okay, so uh, we have which what kind of processor, RAM, memory thing. So this, it acts like mostly like a CPU, and on the end, the on the back we have a battery. So if you ask me that these technology are advanced, or have we achieved what we need, I'll say still there are some problems. So it can be improved. For example, if you take the display technology, we need a wide screen so that the display will be much better. But we can't carry such a wide screen. So we wanted to fold the screen, okay, or roll the screen. So the display technology now is uh, going towards the flexible displays. Okay, and if you come to the second layer, which is the CPU, uh, we are going with a very high speed of RAM. For example, like 8 GB, 16 GB kind of RAM, and very huge kind of memory, like a few terabytes of memory. But if uh, if you ask whether it is sufficient or we can stop, no, we cannot, because the amount of data which we are using, and the amount of processes, amount of work which we are doing, it needs more processor speed, and more data to be stored. So that also materials plays a major role, and it needs the improvement. And if you go to the last session, battery, so one of the major drawback of the mobile phone is the battery. Okay, so you need a long-standing battery, and you need a weightless battery. So for that, again, materials plays a major role. So in this presentation, I'm going to give a brief introduction how materials plays a major role in all these technologies, so that the industry for revolution, because Internet of Things, based on this mobile control, how the materials are going to be useful. So my talk is split into three parts. The first part, I will be talking about the memory storage materials. What are the memory storage available which we were using, and in which direction we are going. And the second part, I will be talking about the display related materials. and how uh, uh, materials can play a major role in improving the display quality. And in the final part, I will be talking about the energy storage material. So that is the battery materials, how we can have a weightless and long-lasting battery. Okay. So before getting into the talk, so I want to take this opportunity, and I will always do this in all my presentation. I thank my teachers, uh, because without their input, their help, we could not have reached this place. So before starting my talk, I thank my teachers, Professor P. Ramasamy and Professor R. Jayawel, with whom I did the PhD in Crystal Growth Center, Anna University. And these are the crystals which we grew during my PhD work, which are not related to this presentation. They are insulators. Um, they are used for IR imaging purpose. I'm not talking about. I'm not going to talk about the application of these materials. And after completing my PhD, as it was introduced, I was introduced, I went to South Korea for a postdoc position, and I worked with Professor Uni Jiang, who is uh, a well-known person in condensed matter physics and materials in South Korea. And this is the institute which I worked, and that is the physics department. And some of the results which I'm going to present here are from the results from this institute. And this is Professor Pont Cubata, and I worked 3 years in Spain, spending my time in preparing thin films and understanding a class of materials called multiferric materials, which I am going to introduce now. And he is the student of Professor J.B. Goodenough, who got a Nobel Prize for a lithium-ion battery in recently 2017. And he is one of the collaborator of Albert Fert, who got a Nobel Prize for giant magnetoresistance material. So I'm going to talk a little bit with their influence. I will be talking a little bit about those materials. And Professor Bell from University of Leeds, I'm going to touch a little bit of results from my UK stay also. So I thank all my teachers who gave me this knowledge, and because without them, I would not be in this situation. So um, uh, before starting, I thank that. That's the gratitude we can show to our teachers. And with their influence, I was working with different fields. So as I said, I started from single crystal growth of different materials, especially optical materials and insulating materials. And then I was working on a class of materials called multiferric materials, which are recently developed materials. I will introduce as the audience are uh, from a different sides, from mechanical, from civil. So I will give a very basic introduction about these materials, and photoferroelectric materials, and self-assembled nanostructure. And recently we are working on these class of materials called low dimensional materials for the display technology, and photocatalysis for environmental uh, protection kind of thing. So I'm not going to touch all these materials. As I said before, I'm going to touch only the three technologies which I have mentioned at the beginning. And I will also give very basic details about these materials, and also I will give the recent results, and also I will present our results on these materials. So before that, to have a device, the engineer should know the engineering parameters. Well, so to have a device, what are the parameters that device should have? So we need an engineer for that. So the engineer then they should tell the physicist. So the physicist will be knowing the phenomenal parameters of those materials. So you need a physicist to know about the phenomenological parameter, and then we need a chemist to know the chemical structure of that material, whether it will be useful. And also, we need a metallurgist to know the physical state, which state is the stable state of that material. So to use a material, we need to collaborate, or we need all these knowledges. Not physicist alone, or not a chemist alone can produce a new material for a particular application. We need your collaboration, engineer, and then we need the industry people to tell what they need. So with all these collaboration, or with all these knowledge on all these subjects, we can work towards new materials, or the materials with different properties. So let me start from the memory storage application. So I hope most of you know this Moore's law, which was proposed in 1960 by Gordon Moore, who is the co-founder of Bell Laboratories. The Moore's law states that uh, with every 2 years, the number of transistors will double. That means the processor speed will increase. Okay. So that was following here. This on the x-axis we have the year, and in the y-axis we have the performance. Okay. So as per the Moore's law, and this is in the logarithmic scale. The y-axis is in the logarithmic scale. So the number of transistors double every year, every 18 months. As per the Moore's law, it's 18 months, the number of transistor will double. So it was following that path maybe up to 2015, and it got saturated. There are some problems. Okay, so the number of transistor increases means the size of the transistor decreases, which I am going to explain a little bit. Okay, so when the transistor size decreases more and more, now we are using 47 nanometer and 7 nanometer transistors. Okay. So that is the minimum size a transistor can have. If you decrease still, there are other problems which come. So that there is a saturation on the Moore's law. And if you take the clock frequency also, it increases and then it saturated. If you take the power, okay, so it was increasing, and then around 2015 it got saturated. So all these technologies are reached this quite minimum part, and it got saturated. So we need to look for either a new material or a new technology, so that the Moore's law will be followed. So here, so the prediction within the year, and the gate physical gate length, as I mentioned, the transistor gate length. So this the blue color is the 2013 report, and the red color is the 2015 report. So in 2013 they predicted it started from 20 nanometer, and now it is close to 5 nanometer. It was the prediction at that time. 2028 we will be going to 5 nanometer technology. In 2015, they predicted like already at 2021 around 7 nanometer it saturated. Okay, so there are quite a lot of problems by which we cannot still reduce the transistor size, so it is saturated. Now we need to look for different materials and different technologies. So this graph shows how we can achieve that with the new materials and more efficient architecture and packaging, or the new models. Okay, so combining all these two, so we know the recently the influence of carbon-based material, quantum dots, graphene. Graphene got a Nobel Prize in 2010. Can produce graphene by a simple method, okay, Scotch tape method. So from 2010 onwards, this carbon-based materials played a major role in the technology development, and then the spintonic materials, which I'm going to introduce a little bit for the electronic application, and then the quantum computing and neuromorphic technology. So with all these technologies, we can still continue with the modes lab. It will not go like a flat, so you can still increase. But the problem with not a problem. But as the speed increases, our patience decreases. Now, previously, when we were using not a very old days, like 15 years back, we had a computer with the hard disk of 5 GB and RAM of 256 MB or 520 MB, and there was a patience. We need to wait for every thing. When you press enter, then the computer will take quite a long time. Now the speed has increased to 8 GB, but we are not that much patient now. So we need the speed to be increased more. So the patience is decreasing as per the Moore's law. Okay, so let me just give a brief introduction about the memory storage, how the it developed. The first hard drive was developed by IBM in the year 1956. It was quite a huge size. Um, so it's a magnetic material based memory, and this graph shows the development of the memory technologies, and of 1970s the floppy disks were introduced, and I hope this generation would not have seen these floppy drives, which I have been using these floppy drives during my PhD work to save my thesis. It can save 1.4 MB of data. Now it has gone to museum, and this is the CD drive, which is also we are not using, and the hard drive size is decreasing. Now we are using like a 2.5-inch hard drive, and in 2017 we have reached uh, the 16 terabyte hard drive, which is quite huge, and the memory data bit is quite small. And the technology from the hard drive, it changed to uh, the SSD. So the SSD, solid state devices, the technology, the principle is completely different than the hard disk drives. Let me not get into the details of this. I'm going to concentrate, I'm going to give a brief introduction about hard disk drives and how it can be improved much better. And this image shows the size of the read and write head. And as you see, from 1 millimeter, it keeps on decreasing. Now it is like a few nanometer. Uh, Let me not get into the details due to the time constraint. Okay, so let me give a brief introduction about this spintronic materials. We know the electronic materials. We have been using the electronic materials. Um, we know that the electron has a charge and also it has the spin. Okay, so the electronic industry or the electronic devices only uses the charge property of an electron. It neglects the spin property of the electron. Okay. So in the spintronic application, the devices using the spin property of the electron. So we are going to see how this affects the memory storage. So here I have given two basic configuration of like spintronic materials, uh, giant magnetoresistance material, for which the Nobel Prize was awarded in the year 2007 to Albert Furt and Peter Gutenberg from Germany. So we have a thin ferromagnetic material. These are all thin films. You have a ferromagnetic materials, and there is a very thin insulating materials here, and there is another ferromagnetic layer. Okay, so if you give some voltage, if a current passes through this ferromagnetic layer, so this ferromagnetic layer will uh, align all the electrons along this spin. Okay. And as this insulating layer is quite thin, the quantum mechanical property will take place. Okay. So according to quantum mechanics, the electron can behave both like a particle and wave. So the electron here will take the wave nature and it will pass through this insulating layer and it will come to this ferromagnetic layer. As all these electrons are having the same spin on this direction, there won't be any scattering and all the electrons will flow through this circuit. So it will have a very low resistance. Okay, so this is one part. So on the other hand, if you have the ferromagnetic layer with the opposite spin, okay, so here if you see the spin is aligned in the downward direction and here the spin is aligned in the upward direction. This we called as antiferromagnetic alignment. Okay, so the spins are aligned anti-parallelly. So here again we are having a very thin insulating layer. So when the electrons pass through this ferromagnetic layer, all the electrons will be aligned in this direction. But when it goes to this ferromagnetic layer, as the spin is aligned in the opposite direction, it will get scattered. This will not pass through. These electrons cannot pass through this ferromagnetic layer and it will get scattered. Okay, so that means the current will not pass through this circuit and it has a very high resistance. So this property we are using for storing a material. Okay, storing the data in a material. And for data storage, we are using the binary storage, zeros and ones. So this state can be the low resistance state, can be the zero state, and the high resistance state can be the one state or vice versa. Okay, so this is the basics of spintronics. And remember, we are giving a current to this ferromagnetic layer. Now that also affects the devices. Okay, so now I'm going to introduce another effect called the piezoelectric effect, which we are going to in my next slide we are going to see how we are going to utilize this effect. as the mechanical, there are quite a lot of mechanical engineers, so they will be knowing and using these piezoelectric material. So when you give pressure to some materials called piezoelectric materials, it will produce voltage. Okay. So for example, in the gas lighters, we are using these kind of material, piezoelectric material. You just give the pressure, and that voltage will, yeah, that's a huge power. That is why it produces the spark, and that is the piezoelectric effect. And the inverse is also true. Uh, so when you give current or potential to these materials, it will expand or decrease. That will change in length. Okay, so that is called as electrostrictive effect, the inverse of the piezoelectric effect. So with that, I'm as we have so far we have been using different materials for different application. Now, as the device size is keep on getting smaller and smaller, we need the same material to to be used for different application. For example, here this yellow color, this is called as ferroelectric materials, where we can apply electric field and change the polarization. And this side, this is called as ferromagnetic material, where we can apply magnetic field and change the magnetization. And this side is called as elastic materials, where we can apply stress and we can change or we can switch the strain. So most of the mechanical engineers, you will be using this type of material, elastic material. And in the first talk, we have heard about the property of these elastic materials. Okay, so the cross property of these three materials, these are called as ferroic materials. So can we switch by applying electric field the strain of a material? Okay, so that is called as that as I explained before. This is called as piezoelectric effect on this direction, or electrostrictive material on the reverse direction. Similarly, from for magnetic materials and elastic materials, we know these technology or these type of material called magnetostrictive materials. You apply magnetic field, there will be change in the strain, or if there is a change in strain, the magnetic moment will be changed. Okay, so this also is very well known. But the cross coupling between the electric polarization and the magnetic polarization was not known, or was not explored, because there are some problems which I will explain briefly. I will not get into the details. Those are called as a magnetoelectric effect, or multiferric materials, which we have been working on that materials for almost 15 years. Okay, so this is again a simple cartoon which explains the magnetically polarizable material here, electrically polarizable material here. You have diamagnetic, paramagnetic, all these, and then we have a ferromagnetic material, and then we have a ferroelectric material here. Okay, so this small circle inside, which has both the ferromagnetic and the ferroelectric, those are called as multiferric materials, which has both the magnetic and electric property. That's the holy grail. And this region where it has both the magnetically polarizable and electrically polarizable are called as magnetoelectric materials. I will briefly explain. I'll briefly explain why it is very difficult to have these properties together. So all these materials, whatever materials we are using, or which we need to be used, should be synthesized from the elements from this periodic table. So if you take a ferromagnetic material, only these materials, transition materials like manganese, cobalt, nickel, iron will have the magnetic property, and in the rare earth you have few rare earths like gadolinium, europium, holmium, which has the magnetic property. But if you take the ferroelectric property, then you have this fifth group elements like titanium, zirconium, niobium. All these will have the ferroelectric property. So there is these two types of materials are mutually exclusive material. So one property will not, one material cannot have both the properties. Okay, so let me give a brief history about this magnetoelectric material. Long back in 1894 itself, Pierre Curie, she predicted that there should be some material which should exist, which can be polarized by a magnetic field and can be magnetized by an electric field. So this is the theoretical prediction which we did in 1894, but she couldn't find any suitable material for that. And until 1937, there are quite a lot of unsuccessful experiments to have this kind of materials. Uh, and as I explained, in a single phase material, to have these type of properties, both these ferroelectric and ferromagnetic properties, quite difficult. So we started working on the nanocomposite material. We call that as a biferroic or multiferroic nanocomposite thin film. So we have a substrate here, and then we can have one layer of ferroelectric material, and we have another layer of ferromagnetic layer. So if you see the top view, you can see both the ferroelectric and the ferromagnetic, two different materials with the two different properties sitting in the same substrate. So the problem now is how one property can influence other. For example, using this magneto electric effect. Okay, so if we give the input of magnetic field H, due to the magnetostrictive effect, so the strain will be produced, and there will be strain in the ferromagnetic phase. Okay, so this strain will be passed to the ferroelectric phase because these two materials are close together, uh, are in contact with each other. So this strain produced in the ferromagnetic layer will be passed to the ferroelectric layer, from which, due to the piezoelectric effect, we can switch the electric polarization. Okay, so by applying magnetic field, we can switch the electric polarization. Similarly, on the reverse also, by applying electric field, we can switch the magnetic polarization. Okay, so we in this thin film, one film which has two different materials, we can control the ferromagnetic material by applying electric field. So we don't need to apply current here. Okay, let me not get into the details again. Um, so by applying electric field, we can control the magnetization. Okay, so what is important here? It is the elastic coupling between the ferroelectric and the ferromagnetic phases in these material. Okay, so these materials were prepared, or epitaxial materials were prepared by technique called pulsed laser deposition. This is a cartoon. The laser falls on a target which has both the ferroelectric and the ferromagnetic material. As the laser energy is quite huge, the plasma will be produced. So if you put a substrate um, with the optimal temperature, we can produce epitaxial thin film, which can have both the ferromagnetic and ferroelectric materials in it. Okay, so these are called as multiferroic heterostructures. So if you see on the top, this is the atomic force microscopy image. So these are called as cobalt ferrite, which is a very good magnetic material, and the matrix is the ferroelectric material, which is called as a barium titanate, which is the um, model ferroelectric material. Okay, so this is the XRD, the technical data. So this is the epitaxial thin film. So what I want to insist here, this is this material, this thin film has both the electrical polarization and magnetic polarization here. Okay. So this is both ferroelectric and ferromagnetic. And also, so one, if you change the temperature, the the magnetization changes along the ferroelectric polarization. So there is a quite a quite a good elastic coupling between the ferroelectric and the ferromagnetic materials. Okay, so and now we can have in a single material, not a single phase material, and a single thin film, a material with both the ferroelectric and ferromagnetic properties. Okay, so why we need to have a multiferroic materials, because it can produce the very high density of a memory that can be solved, the higher density of circuits. Okay, so the number of transistors can be increased. As I said, the problem with the speed can be increased. The access time can be increased. So all these are the applications of multiferroic materials, and these are the publication number of papers, which is increasing quite recently now. Okay, so as I said, the speed can be increased. So we know that light is the fastest material which we know. So can be, and I also showed that the main property to have this ferromagnetic and ferroelectric coupling in a single phased material is this elastic coupling. Okay, so can we use light to change this elastic coupling, so that we can switch the electric, or you can read and write with the speed of the light? Yeah, there is the answer. We have a material called photostrictive materials. Okay, so with these kind of materials, the read and the write speed of the materials can be increased, and the research is going on these kind of materials recently to increase the writing and reading speed. Okay, so again, this is uh, explanation about how the light can be used. Let me not, due to the time um, problem. Okay, let me briefly come to the next part, which is the display materials. Let me time is already. Okay, so I will quickly go through these display materials. Okay, so um, recently we have been using the display materials. If you go to the television screens, we have been using the CROs, or electron tubes, and then it came to liquid crystal displays, and then LED displays, and then if you see the technical terms in displays, they will be using like terms like AMLED, OLED, organic LEDs, and AMOLED. In the mobile screen, you can see all these technical terms, which are all active matrix organic LED. So now apart from all these, now we are using quantum dots. Okay, for display materials, quantum dots are materials which have very in the length scale, it is less than 10 nanometer. Okay, so the quantum effect comes to play. So now we are using quantum dots called cadmium selenide, zinc selenide, all these properties. And you can see the materials, the quantum dots can produce all the color range from blue to orange to red. Okay. So with these material, the pixel size can be increased and the quality of the display can be increased, and we can have a curved display or foldable display or even flexible rollable displays. Okay, so based on these materials, there are some problems with selenide, sulfide, cadmium. All these are toxic materials. So research is going on how to remove these toxic materials and quantum dots to produce useful display materials. And in our first presentation, and on the first day, Sir was Armugam sir, I think he introduced a material called perovskite material. So that for cooling technology there. So that material is quite an amazing material which can be used for quite a lot of application, not only for cooling application. So we have been working on that kind of a material for display applications. So this type of a material, they are called as a perovskite material, and it can be used for so many applications like transistors, detectors, and spectral tunabilities, LEDs, and then as they are quantum dots, so we can tune the band gap to produce different colors. Okay, so we are working on these kind of perovskite quantum dots, and we could produce few papers on these materials. Quite interesting material. Let me not get into the detail. Okay. So as I mentioned at the beginning, so our institute is closely situated around industries, and there are quite a lot of environmental pollutions. So we are also working on materials called photocatalysis, catalytic materials to avoid these pollutions um, by carbon capturing and organic pollutant reductions. Let me not get into the details due to the time constraint. I'll just skip this part. Okay. So on my final part, I will just quickly complete get into this energy storage materials or the battery materials. We all know that the batteries which we are using are electrochemical batteries, and it was discovered by Alexander Volta. So he put a series of copper and zinc metal. In between, there is a thin paper with the electrolyte, and he could produce. He could store the charge. That's why this is called as voltaic cell. And then it developed into the Daniel cell, and the lead acid cell came into use in 1959. Still, we are using the lead acid batteries for quite a lot of application for and then zinc carbon battery, and recently we are using lithium ion batteries and the nickel cadmium batteries. So in this lithium ion batteries, even though the technology is well developed, we have been using this for almost 4 decades now. The problem is the availability of lithium. So China is playing a major role for lithium ore, and they are controlling. So we need to change the direction from the lithium ion batteries to some other direction. So we are working on the on that direction also. So this explains how a simple electrolyte cell works. Okay? So you have an anode, you have a cathode, and you have a electrolyte in between. So oxidation, which is the loss of electron, occurs at the anode. So the electrons will flow, and the reduction occurs at the cathode. This is the basic principle of any sorry, electrolytic or any electrochemical cell. So this graph shows the roadmap of how this battery technology can be increased, okay, from lithium and battery, which is having a few terawatt per hour, uh, 2030 how it is going to be, and 2035 how we need to be having. And the problem with the lithium ion battery is you would have heard that fire occurring because of the electrolyte. There are dendrites, and there is some growth called a dendritic growth, and there is a shortcut occurring between the electrode. That's why the fire occurs. So we need to work with the solid state batteries. We need to have a solid state electrolyte. So we are working on that one, oxide electrolyte, so that we can have uh, all the anode, your electrolyte and the cathode as a solid. We can have a solid state batteries to avoid that firing and all these things, the battery problems. Okay, so as I said, these are the some of the materials which are used for the electrochemical batteries. We have the anode material, lithium, silicon, graphite, and lithium tantalite, and the cathode material, nickel, manganese, cobalt, nickel, cobalt, aluminum, sulfur, all these materials. So research is going on how to optimize these materials to produce very good batteries, and then solid electrolytes. So we are working on this oxide electrolyte, so that we will be having all the materials in a battery to have to be solid. So this gives what are the challenges in the oxide electrolytes, and what are the possible solutions. Um, Let me not get into the details. The problem is the brittleness, centering temperature, um, and then performance, uh, the lithium stability, and then how to process this thin in a thin film. Okay, uh, so research is going on this direction. These are the possible solution, and there are recent reports which shows that all oxide, solid oxide electrolyte can be used for a better battery. And then the research direction is also going towards the sodium ion batteries to avoid lithium and the problems created by the lithium. And this is another type of material called supercapacitors, electrochemical cell. Okay, there is a small difference between the battery and uh, these supercapacitors. Okay, so these slides I took from the recent FDP given by the industry people called surge supercapacitors, and these are the materials called MXenes. Okay, so and these are called as two-dimensional materials, layer by layer materials, and these materials are used for supercapacitor applications. Let me not get into the uh, details. So in supercapacitor, it can store quite a lot of charges. These are not normal capacitors. These are also called as double layer capacitors. Okay, again, the materials involved on these supercapacitors, we have electrodes and electrolytes. And the electrodes, we can have the nanostructure carbon-based material, activated carbon-based materials. On the on anode side, we can have the metal oxides, manganese dioxide, nickel oxide, all these materials for electrodes. And if you see the electrolyte, we have quite a huge number of possible electrolyte materials. Now we need to find the correct combination of these materials which will give very good supercapacitive property, and the research is going on that direction nowadays to find the correct proportion and correct combination of these materials. Okay, so if you arrange I will quickly finish. I'm pressing the time. I will quickly finish. So if you arrange the supercapacitors in a parallel way, so this is the voltage and this is the current the density. So if you arrange parallel, you can see the voltage is the current density is increasing. Okay, the current density is quite huge and the voltage remains constant. But if you arrange in a series these supercapacitors, um, the voltage increases and the current density almost remains the same as this one. This is the original one, so the current density remains the same. So if you want to have both the very high current density and a very high voltage, we need the combination of both the parallel and series, so that the voltage we can have both the voltage and the current density increase. So that we need to find a good combination to have very good voltage and current density, so which can be achieved by arranging the supercapacitors with both parallel and series. So with this, I come to the I want to summarize that there is a huge possibility based on the materials to on increasing the processor speed and internal memory and the display with the new materials and new technology. And also, I want to thank my students and my collaborators with whom I'm learning from recently. These are my PhD students, Dr. Yan Ramu, who worked on these multiferroic materials, which I was mentioning at the first part of my talk, and Dr. S. Ganesan, who worked on the perovskite materials, which I explained in the second part, and Mrs. Hemalata. This is she worked on the um, uh, uh, ferrite material for a biomedical application, which I am not mentioning here. And these are our collaborators from SRM University. Recently, I am working with these people on quantum dots and low dimensional materials for display materials. And thank you. And I thank again the organizers for giving me this wonderful opportunity to share our results. And if there is any questions, suggestions, I will be very happy to take that. Thank you.
Thank you, sir, for your wonderful, valuable
Thank you, sir.
information.
Thank you, sir. Thank you. So if there is any question, I will be very happy. Will they post the question in the chat box, or is there any
Secretary,
questions in the chat? Okay. Why steel
sir,
is not used in columns and the beams for construction? Uh, And I'm sorry for that. I'm not the right person to answer this question. We have a wonderful, eminent persons from the industries who have talked about the steel property. Maybe this question can, through the organizers, can be passed to that sir who was presenting on the third day, I think, who talked about steel. So I'm sorry. Mr. Vijay Manigandan about that. So you pass that question to the organizer, they can pass it to the other speaker who talked about steel, so that you will get the answer. Sorry for that.
Sir, good evening.
Good evening, sir. Yeah.
Sir, what about this lithium? Because we are recent days we are talking again and again about lithium because EV vehicles are going to come, so the lithium batteries are needed like that. But what is the
Yes.
availability of lithium in the Earth's crust? So how
Uh,
well
that,
we can?
that is what I mentioned, sir. So, lithium ion technology is a well established technology, and we need to we can't supply as per the demand. If the electrical vehicle comes, as you mentioned, we cannot supply that much of lithium because the lithium ore is very less. So we need to find an alternative. That is why now people have started working on the sodium ion based materials. Okay. So the advantage is the sodium ion batteries, again, the technology wise, it is very similar to the lithium ion batteries. So we don't have to switch to a completely different technology. We can follow the same technology as the lithium ion batteries. For the sodium ion batteries, the advantage of sodium ion batteries, as you said, we have tremendous amount of sodium available everywhere. So there won't be any particular region where this sodium is available. So throughout the world, so all over, we can use this sodium. The problem with the sodium is the ionic size is bigger. So if you want to compare the um, property with the lithium ion battery, the sodium ion battery will have the less property because it has the we need to have more space to have this sodium ion battery. But recently there are research going on this sodium ion battery and zinc air battery, in which we can go very close to lithium ion battery. So soon, I think we can replace lithium with some other metal, like a transition metal, like sodium or zinc based materials. So research is going on that direction, sir.
Obviously, the cost will be low, sir. Sodium or zinc, if you
Yeah.
are.
Again, if you say, yeah, the cost will be very less when compared with the lithium ion batteries. So we need to compromise a few things, like for a size based. So if there is no restriction for the size, for example, in the electrical vehicle, we have the restriction for the size. So there are some applications where we can there is no restriction for space, like for a grid application. So for that application, we can replace the lithium ion batteries with sodium ion batteries, so that we can reduce the lithium usage. And also we need to find a suitable recycling procedure for lithium ion batteries, so that the lithium can be used, the recycled lithium can be used. So research is going on that direction also, how to recycle the lithium ion lithium for using again. That's fine. Thank you, sir. Thank you, sir.
Thank you.
That's a good
Thank you.
question, sir. Thank you. So I think if there is no more question, I thank again the organizers and the management of Sakthi Engineering College for giving me this opportunity to share my knowledge with this august audience. Thank you so much. Sir Nandagopal sir.